All right, so in this video, we're going to look at how to conduct ANOVA tests in R. Now, one of the things to keep in mind about conducting ANOVA tests in R is that R likes data frames. And so when we do analysis of ANOVAs in R, we also need to keep our information that we're analyzing in a data frame. Now, in other programs, you may be familiar with the way the TI-84 works. You may be familiar with the way analysis works in Excel. You may have run into this in some packages in Python. They want you for ANOVA tests to separate the data into different lists, and then the analysis is done based on those 3 or 4 lists that are entered into the program. Now, that is not the way that ANOVA works in R. In R, we want the data in a data frame where all of the numerical observations are in a single column. And in a second column, we have the categories that the treatment counts that these represent in factor form. If we are doing a 2-way or a 3-way ANOVA, we will have additional columns of factors that will indicate how the data is sorted into different subsets. Now, this is definitely different than the way ANOVAs are typically presented, not only in other programs, but in the way they're summarized in textbooks. So you may have to do some conversion into a data frame before you can perform your ANOVA analysis. Now, we're going to work with the MT-CARS data set that's built into R, which is already in the required format. We have several variables that can be considered categorical or at the very least discrete, which we will treat as categorical variables, and we will transform those variables into factors. And all of the numerical observations that we're going to try to model are also in a single column and not in multiple subsets. So let us first begin by pulling in our data, MT-CARS. And we have seen this data before, so if we want, we can go ahead and view the data set just to, again, confirm the way that it looks. So for instance, the cylinders, these are discrete values. They can only be 4, 6, and 8. They can't be 5 or 7, for example. So we should treat this as categories rather than as a continuous numerical variable. This will be a good example for our categories. We could also use these 0, 1 variables, or these number of gears, or the number of carburetors. This carb variable are also, again, numerical, but discrete. And so these will also make good factor variables. These other numerical variables like MPG, displacement, horsepower, quarter mile second in seconds, and so on and so forth, the weight, these are all continuous variables. These are things we should be modeling with ANOVA and not putting in as factor variables because there's just too many values for them. But things like cylinders and whether it's automatic or manual and the number of gears that it has and so forth, these are all good discrete variables that we can turn into factors. But notice that the way it's organized, this is the way that we want the data to be in R in order to do the analysis. We do not need to then pull these apart into separate vectors in order to perform our analysis. So this is how we want all of the data to be. So what I'm going to do, because ANOVA wants variables, their category variables as factors, we're going to convert the variable cylinder into a factor variable. So MT-CARS cylinder, we're going to factorize that. And again, what this just does is that it treats it like a text string rather than a number so that we can import it into our ANOVA. One way, since we're going to start with our one-way ANOVA, and then we're going to use the ANOVA function AOV. Now, this is not the only way that you can do ANOVAs, and in fact, in a much later video, we'll actually look at an alternative. but we're going to model MPG based on the number of cylinders. So our cylinders are our category variable, and MPG is the numerical variable we're trying to predict. And we're going to pull our data from the mtcars package. And when we run that, that saves the model as one way. And then we can do our analysis of it. We can extract various components of it, and we can look at a summary. And so this is our summary analysis. We can see the ANOVA table here, the degrees of freedom, the sum of squares, the mean square error, the F value, and then the corresponding P value, which is quite low. So this indicates that since this is much less than 0.05 or any other significance level, we might suggest that we can reject the null hypothesis. What is the null hypothesis? For ANOVAs, the null hypothesis is that all means are the same, and the alternative is that at least one mean is different. Now we have 3 cylinder levels here, 4, 6, and 8. So there's 3 cylinder levels. And what we're saying is that at least one of those is different. Now, one way that we can assess which one is different from the others is that we can look at a comparative box plot in order to see what that looks like. That won't be the best evidence of distinction, but that will give us some kind of a hint, at least, and help us visualize what's going on. So we're going to do this in ggplot. ggplot. Data is mtcars. What do we want to plot? X is MPG. Y is cylinders. And we're going to do a geom box plot. Oops, I can spell. And then we're going to add some labels. Title, box plot of MPG by cylinders. XLab, miles per gallon. YLab, number of cylinders. And so here's our graph. Now this makes it look very clear that the likely result of our analysis is that all of these 3 levels are different from each other. Not just 2 of them are the same and 1 of them is different, but that they're literally all different. You can see that the central 50%, the interquartile range, none of these overlap at all with each other. The box plots at all barely overlap with each other at all. So this is going to suggest that in fact there is a strong distinction between these variables, which is why the p-value is so low. Now, to do a slightly better job of the distinction and making sure that we know exactly what the difference is, particularly if in the case where our I lost my train of thought, where our overlap is not quite so clear, where it may be a little bit fuzzier as to exactly what the difference is between the variables. Are we talking about a real distinction because of the number of samples, or are we talking about one of them is overlapping another one, but then there's a third one or a fourth one that is much different, or at least sufficiently different. So sometimes you can sort of discern that, as we can see here from the box plot, but you can't always do that. And so you want a little bit more information about how these actually separate from each other. And so to do that, we can do a Tukey test. We can essentially construct confidence intervals around the means of each of our data sets, our subsets, for each of our cylinder levels. And then we can see how they overlap or how the differences between them overlap with 0. So we're going to pull in another package. This one is called multcompview. And this is the package that's going to have the Tukey test in it. Now, if you have not obviously installed this, used this package before, you do need to install it before you activate it and load it to run. And so we're going to calculate our Tukey test, one-way ANOVA, on our ANOVA analysis that we did before, Tukey HSD on one-way. And then we can print the results. Like so. So what we can see here is we have intervals that are specified between the various different categories. So the difference between 6 cylinders and 4 cylinders, the difference between the means is about 6.9. The lower bound for that confidence interval is -10. The upper bound is -3. That does not include 0. And so the adjusted p-value for this confidence interval is 0.0003. The difference between 8 and 4 cylinders is -11. The lower bound is -14. The upper bound is -8. And we can see that the adjusted p-value for these are very different from each other, is almost 0. More lower than what the threshold is of the calculation. And then the difference between the 8 and the 6 cylinders, the difference is smaller. It's only -4, but the lower bound is -8 and the upper bound is still just about -1. And so even though this has the highest p-value, it is still statistically significant. So this will give us, again, not only the differences between the intervals, but it'll give us a confidence interval and an adjusted p-value to give us a sense of whether we can consider these statistically significant or not. Now, we can also plot these intervals so that we can visualize them. So we're going to plot Tukey 1. And when I run that, what I get is a confidence interval plot. And again, when you're looking at these and comparing them, you want to look for where the 0 is. In this case, the 0 is all the way off the graph. And so none of these overlap with 0. But if 0 were, say, right here, then we would be able to say, well, these two overlap with 0, so they don't count as being different. But this one would not overlap with 0, and so it would count as being different. So that's how you would interpret this graph. Now we're going to add another variable to our analysis and go up to a two-way ANOVA. So we're also going to take the gears variable and turn that into a factor. This gear. And then we're going to do our two-way ANOVA, which is basically going to work pretty much the same as the one-way ANOVA. We're going to use the same function. MPG is being modeled by, and then we just put a plus sign in between our two variables. And then we can get the summary of our two-way. Now here, we're only considering the main effects of our two-way model. We see our degrees of freedom. There are also 3 levels of gears. And we can see our p-value for the cylinders is still quite low, but the p-value for the gears is actually 0.68, which is way above any significance level that we would want. So this would indicate to us that there is, in fact, gears are not statistically significant, and we could go back to the one-way model, or we would have to choose another variable. Now, another way that we could analyze this is with interaction effects. And so we could construct an interaction effect basically by, instead of using a plus sign in between our variables, if we use a multiplication sign, that will indicate that we want to test not only the cylinders and the gears, but also the interaction between the cylinders and the gears. And then we can look at the summary to see what the results are. And since the gears were not statistically significant, the interaction between the gears is also not statistically significant, and that should not particularly surprise us. We can also continue adding more variables for analysis. So for instance, we could have a three-way ANOVA or n-way ANOVA by simply including additional variables. So for instance, we could add the carb variable and the AM variable, and then since we know that cylinders is statistically significant, we could see if how these interact with, let's say, the gears, for instance. So let's convert our variables into factors. And then let's try our three-way. MPG is being modeled by gear plus AM plus carb, and data is MT cars. Now we know that the gears variable is not statistically significant when included with cylinders, but it may be statistically significant when it's done either by itself or with some other variables. So we can explore that relationship. Here's our three-way ANOVA. And in fact, that is in fact the case. Apparently gears and cylinders may be, I would say, collinear, that they have a relationship with each other. And so when used together, gears is statistically not significant, but when done by itself or in combination with other variables, it does in fact matter. Here we can see that all of our p-values are actually below the standard significance level. And so we can therefore actually in this model, the three-way model, that does not include cylinders, we could actually keep all three of these variables. And if we wanted to do the interaction terms that are possible from this model, we could continue to replace this with a multiplication sign. So if we wanted to do the full interaction model, we can do this. And the interactions that are available will be analyzed. Now, it may be that there are no distinctions, there may be no subcategories. We only have 32 observations in this data set. The more interactions that you include, the more data you generally need, or you need to be very careful to make sure that you've included all the possible combinations. In this case, there isn't enough data to, not in terms of quantity, but in terms of the specific interaction components to get all three interactions at the same time. simultaneously to see if they combine with each other. We do have two examples of two-way interactions, but there could, in principle, be a third one. So we don't see any interaction here between gear and automatic or manual, which would be the third version of the two-way interaction. Again, the data just isn't there for that. But what we can see is that our interaction terms in this case actually have very high statistical significance. And so this suggests that the interaction terms are not significant even when they occur. And so we don't actually need these interaction terms. The main effects from our previous model actually do the job quite nicely in terms of modeling our MPG. Now, when we do a Tukey test on this, using Tukey's method to get our intervals, we can do that. But of course, the graphs are going to be a little bit more complex, and there's actually going to be several of them. So let's actually look at that. We'll do our original three-way Tukey without the interactions. Tukey HSD. And we're going to do that on the original three-way. Oops. And then we're going to plot the results rather than look at the outcome first. Tukey 3. Now, this is the mean differences in levels of the carburetor, the carb variable. So there are several levels of this, and you can see what each of them are doing. And you can see here's the 0 on our line that we were talking about. And if we have intervals that are fully on one side of the line or the other, then that is a difference between the two levels that is statistically significant. And so you can see here, there's a difference between 4 and 1 is different. This one, 8 and 1, it looks like it maybe comes right up to the line, but it might be statistically significant. 4 and 2, definitely significant. And again, you only need one of these to not overlap with 0 in order for the factor to be relevant. Now, if you go back through your graphs, you'll actually see differences, graphs that you missed that were also plotted. So here, this is the different levels of automatic versus manual. This one is not statistically significant in this case because it includes 0 in the interval. And then this one in levels of gears, again, we have 2 intervals that do not overlap with 0 and 1 that does. So the difference between 5 and 4 gears is not statistically significant, but the difference between 5 and 3 gears or 4 and 3 gears is. And then this was our graph from earlier. So it will plot one graph per different variable, how the different levels are. And if you include the version with the interaction terms, it'll also plot graphs of the interaction terms. And what we would expect to see if we plotted the three-way with the interaction, we would expect 2 more graphs at least for these 2 interactions. And what we should see is that all of the intervals overlap with 0. Now, when you start doing these interaction terms, you have many, many more levels because you have different combinations of all of them. And so sometimes the graphs can be quite dense and difficult to read. So I'm not going to go there. But if you had the interactions that were significant, then you would definitely want to look at that. Now, you can also, as we saw earlier, you can also print out the interval levels. So if you just print the name of the Tukey, in this case, Tukey 3, then it will print out to the console all of the actual intervals and their individual p-values. So here we can see the gear variables. The p-value for 5.4 is not low enough, but these two would be low enough. This one, this is around 10%. So it's a little high, which is why it overlaps with 0 for our 95% confidence interval. And then similarly, we see some of these p-values are quite high because there's not really a difference. But in terms of some of them, we do see some of these intervals that do not contain 0. So this is both ends are negative, and this p-value is quite small. This one just barely at the 95% confidence level crosses 0, so it's not fully negative. And then we have one other one here. This one is fully negative. But you can see from the p-values, sometimes they're just a little too high, and sometimes like we're not even messing around here. The p-values are extremely high, which indicates that there isn't a distinction between those. Now, the alternative for looking at using the Tukey method to distinguish within an ANOVA, once you reject your ANOVA, how are they actually different from each other? The alternative is to do multiple two-way t-tests. So for instance, if we were doing the automatic versus manual variable, the AM variable separately, then we could just do a two-way t-test because there's only 2 levels. But if we were looking at like the cylinders, there were 3 variables, 3 factor levels, we would have to do 3 two-way t-tests in order to distinguish them one by one. So this Tukey method is a different way of giving us our analysis to see how do these things overlap with each other or at all. And so sometimes you can see in these graphs some things overlapping with each other. So for instance, you may find that some of the levels, again, the 5 and the 4 are similar to each other, but the 4 and the 3 are quite different from each other, and the 5 and the 3 are quite different from each other. So there are some subgroups that are quite distinct, and then there are some subgroups which may in fact share some information or may not be statistically distinct. And so you may see in other books where they will visually try to represent the relationships between these variables by indicating with underlines or other kinds of grouping mechanisms how the levels of our factor variables do or don't differ from each other.